All right, so I hope we can see the screen now, full screen. Can anybody just respond so that we can proceed quickly?
Yes, we can see it.
Oh, great. So an introduction to health physics. So just a little information about myself. My name is Oluwatobi Adediran. And I currently hold a master's degree, a Master of Technology degree in Radiation and Health Physics, and a doctoral researcher, and as well as a lecturer at the Federal University of Technology, Akure. And my research interests are radioecology and environmental radiation protection. I hope as time goes on, many of the participants, especially the undergraduate students, will become familiar with these fields in radiation protection. Okay, so we are looking at an introduction to health physics. What do we mean by health physics? Now, yesterday we looked at introduction to physics in healthcare, and that is quite close to health physics. But specifically, health physics is the development, dissemination, and application of scientific knowledge and practice for radiation protection. So the important thing to note there is that health physics can actually be described summarily as radiation protection. And the objective of health physics is the protection of man and the environment from unnecessary exposure to radiation. So basically, when we are talking about health physics, the key word to note is radiation and radiation protection. So health there actually has to do with radiation health. So we can introduce an adjective in our minds to say radiation health physics. Now, one will wonder what the difference is between health physics and medical physics. Now, medical physics is the broader horizon that has to do with the application of physics in medicine or to medical health. And so that doesn't just have to do with radiation protection. It could cover many other areas, whether you're looking at imaging or treatment, whether you're looking at diagnostics or therapeutics. Any application of physics to medicine will come under medical physics. But under health physics, we are basically talking about radiation protection, the protection of man and his environment. And there are many organizations, just like you can see on the slide, that are overseeing health physics nationally and globally. IEA, which we may already know, the International Atomic Energy Agency, IRPA, UNSCEAR, WHO, the World Health Organization, ICRP, and then HPS, Health Physics Society. So these are just some of the organizations that are interested, that have objectives that are channeled towards health physics, or what we can call radiation protection physics. So what are the branches of health physics? Well, the branches will depend on the organization, or put in another way, the nomenclature for the branches would depend on the organization in question. So we're just going to look at one organization, ICRP, the International Commission on Radiological Protection. As a branch, we have radiation effects, which basically has to do with the risks that are associated with radiation. So since we are talking about radiation protection, what are the risks to humans and then to possibly the environment or other species as a result of exposure to radiation? Then we also have dosimetry, which has to do with how we can acquire data with regards to radiation protection and come up with mathematical models and what we refer to as dose coefficients. Now, these are terms that we may not be familiar with, but it is important that we just know these branches. Then there is another one which we find very exciting for this school, which is the medical exposure. So the branch of medical exposure is biased towards radiation protection in medicine. And this does not just apply to patients, it also applies to staff and also to the public. So sometimes you have medical exposure and then the public is also affected. So the application of radiation protection in the field of medicine is also a branch. And then we have another field that has to do with the recommendations, communication of radiation effects to the public, and then environmental protection, which is actually my area. So basically, two fields, two branches here are of utmost importance: medical exposures and environmental protection. The other branches in terms of radiation effect, dosimetry, and applications are applied to the medical exposure and the environmental protection. So what then is radiation? Radiation is the emission and propagation of energy through a medium. So once we have energy transmitting through the material medium, then we refer to that transmitting energy or the propagating energy as radiation. And this radiation could be in two forms. It could be in form of waves or particles. So when we're looking at radiation in form of waves, we're looking at electromagnetic radiation. And then for the particulate radiation, we're looking at what we refer to as corpuscular radiation. So what are the electromagnetic waves? From first principles, we know that electromagnetic waves do not require a material medium for a propagation. So we can just take a look at the spectrum that is currently shown on the slide. So from right to left now, we can see the spectrum in increasing energy. And then from left to right, we can see increasing wavelengths, to suggest that the shorter the wavelength, the higher the energy. So we can see radio waves, infrared, the visible light region, ultraviolet, X-rays, and gamma rays. We have some other electromagnetic waves that are not shown here: the extremely low frequency, the very low frequency, and so on. But the important thing to note here is that the electromagnetic waves actually constitute a spectrum that can be described by their wavelength or their frequency or their energy. So depending on the wavelength, frequency, and energy, we can group these electromagnetic waves in different windows that have been shown in the slide. So in health physics, what kind of electromagnetic waves are we interested in? Now, electromagnetic waves or radiation can either be non-ionizing or ionizing. So non-ionizing radiation do not possess sufficient energy to produce ions, while ionizing radiation, which could also be photons or particles, have sufficient energy to produce ions in their medium of propagation. So basically, in health physics, we are mostly interested in the ionizing radiation because of their energy, which will result to ionization, the production of ions in atoms that constitute the medium with which they are traveling. So if you look at the diagram on the slide, you'll see on the right-hand side, the ionizing radiation shown: X-rays, gamma rays, and cosmic rays. But again, these are the electromagnetic radiation under ionizing radiation. So for ionizing radiation, we said it can constitute photons or particles. So when we're talking about photons, we're talking about X-rays, gamma rays, and cosmic rays. For the photons, which are ionizing radiation and which are also electromagnetic in nature. So basically, for the ionizing radiation, which we are interested in health physics, we have the particulate ones and the electromagnetic ones, which we have mentioned initially. So for the particles, we talk about alpha, beta and neutrons, alpha particles, beta particles, and neutrons, which of course have masses. That is why we are saying that they are particulates. And then the electromagnetic, which means they can propagate in vacuum. Examples are the gamma rays, X-rays, cosmic rays, and so on. So two groups, the corpuscular or particulate and the electromagnetic. So what are the properties of this ionizing radiation? Mostly the properties can be grouped into, generally, their penetration and ionization tendencies. Don't forget, we have said ionizing radiations have sufficient energy to produce ions. So generally, alpha particles have the lowest penetrating powers. So we can see in that figure that they can be stopped by a sheet of paper, followed by beta particles and gamma rays. Gamma rays have the highest penetrating powers. And the penetrating power is inversely proportional to the ionization power. So the higher the penetration, the lower the ionization tendency. So while alpha particles can be stopped by a sheet of paper, they are most ionizing, and that's why they are stopped. During the process of ionization, while they lose energy to keep propagating in the medium. So it's not just about looking at the penetration. You have to look at the ionization, which is actually the most important. So the least penetrating is the most ionizing, and that makes alpha particles the most ionizing of the particulate ionizing radiation. What are the sources of ionizing radiation? It could be natural or artificial. So in the second slide, I said radiation is ubiquitous, which means radiation can be found everywhere because of natural sources. So radiation comes from the outer space, from rocks, from water, whether water that is consumed, or just open water bodies, all release natural radiation. And radiation could also be from artificial sources, such as X-ray tubes, nuclear reactors, nuclear weapons, and so on. So in health physics, we're interested in the natural sources and the artificial sources of radiation to look at how we can protect man and his environment from both natural sources of radiation and artificial. And all of them are important. One is not more important than the other. This ionizing radiation, since we said they have sufficient energy, while they pass through biological tissues, they impact energy. And while they impact energy into the biological tissues, they result to chemical changes that can lead to different health detriments, such as skin burns, cancer, and even death. Now, these radiation health detriments can be genetic or somatic. And what do we mean by that? There are some detriments that reveal themselves in the recipient of the radiation directly. Once a person receives ionizing radiation, the effects are revealed in that person. And so we'll talk about the somatic effects. But for the genetic effects, people can be exposed to radiation and the effect will not be evident in them, but the effect will be evident in their children or grandchildren, as the case may be. So this kind of effects are referred to as the genetic effects of radiation. And that is why it's not sufficient to characterize the effect of radiation on the recipients. It is good enough to keep monitoring even the progenies so that you can know if some of those effects were only hidden in the recipients and revealed in their children. So biological effects, still talking about the effect of ionizing radiation. Good enough, sometimes the effects are not observable. You may not observe any damage. And then sometimes the cells that receive the radiation could be damaged and could undergo repair. So there is a cell damage. Possibly the damage is not enough to cause a malfunctioning of the cells or the cells to get repaired. And then this radiation could also affect the cells and cause them to function abnormally. If you look at the diagram on that slide, you will see that the radiation is affecting the DNA structure, causing a breaking. Sometimes we talk about the single strand, the double strand breaks, and so on. So sometimes the breaking could be repaired, sometimes it won't be repaired. And then it can also lead to cell death. The cells may completely be destroyed as a result of the radiation. Basically, the effect that will take place depends on the type of the radiation and the amount of the radiation that is received, which is basically characterized by what we call the dose. So depending on the type of radiation, the ionizing tendency of the radiation and the dosage received, maybe within a short period of time or within a length of time, we can find any of these biological effects. Now, in radiation protection, we talk of exposure. We have been talking about exposure right from the beginning of this presentation, but we also have what we call contamination. Now, radiation and contamination are relevant to health physics, but they are different. When we say exposure, we only mean that people have been exposed to radiation. People have had contact with radiation, but not direct contact with the sources of those radiation. They have only been exposed. They have received the energy. Yeah, that would be a good description. They have received the energy from the sources to their bodies. So we talk of radiation exposure. When we talk about contamination, it means that there has been a direct interaction with the source of the radiation, such that those that have been contaminated can also expose others. So contamination is interacting with a source of radiation, and then you yourself begin to radiate, so you can expose other people to radiation from yourself. So if you look at the diagrams, you see that for the first one, exposure just has to do with the release of the radiation, while contamination, the person who has been contaminated also exposes other people, so it becomes a more severe case. We also have what we refer to as irradiation and activation, which are also kind of exposure, talking about different classes of exposure. So irradiation, deliberately you are exposing a material to radiation in order to change some qualities of the materials. But in activation, you have a non-radioactive material being exposed to radiation so that it can become radioactive. So there we talk about activation, when a non-radioactive material is exposed to radiation and then it becomes radioactive itself. So in health physics, what are the kinds of exposure situations we can have? Exposures may be planned, so it's not all exposures that are accidental. Sometimes you have a planned exposure. Maybe you want to handle a radiation source in the laboratory, in the hospital, or what have you. It is a planned exposure situation, and health physicists have to take note of the peculiarities of that kind of exposure, so that it can be handled properly and so that the outcome can be achieved. Exposures may also be emergency, which are unexpected situations. For example, we could have a nuclear accident, such as the Fukushima accident, Chernobyl, and so on. So these kind of situations are unplanned, and despite the unplanned situations, health physicists have to intervene, and those kind of exposure situations require urgent attention. And some exposures are existing. The existing exposures basically have to do with natural exposures, exposure to radon in houses, exposure of aircrew to cosmic radiation, naturally occurring radioactive materials, and so on. So 3 exposure situations: planned, emergency, and existing exposure situation. So in health physics, there are radiological units that we should be familiar with. The most fundamental is disintegrations per minute, Curie, becquerel, and count per minute. All these have to do with activity measurement or radioactivity. They could be in any of those. And then we're talking about radiation exposure. Some of the units we'll come across are the Röntgen, Gray, the RAD, REM, and CVETs. All these are radiological units for activity concentration and for dose. So when we talk about radiation exposure or radiation exposure rate, we are basically talking about doses, radiation doses, for which we also have different types, different classifications of doses. We can talk of the absorbed dose, the dose equivalent, and the popular effective dose. So whatever dose we are talking about, basically you can express them in this unit. But most popularly, talk of the sievert as the unit of radiation exposure measurement. A very important physical factor to characterize radiation exposure or radionuclides, actually, these atoms that emit radiation, is their half-life, which is the time taken for the amount of radioactive material to decrease by 1/2 to become half of its original amount. So the half-life is very important. It's a very important qualifier or property of these radionuclides. And the shorter the half-life, we'll see some examples of radionuclides and their half-lives very shortly. But the shorter the half-life of the radionuclide, the more active it is. It simply means that it is reducing to half of its original amount very quickly. So when the half-life is short, it simply means that the activity is quite high. And when we have very long half-lives, for example, for primordial radionuclides that have been existing since the origin of the Earth, then it shows that the activity is actually low. So that is important for us to note. So examples of radionuclides: cesium-137, cobalt-60, plutonium-239, iridium-192, iodine-131, and so on and so forth. So we can see that the first thing that describes these radionuclides is their physical half-life. Physical is there because we also have what we refer to as the biological half-life. But let's just focus on their physical half-life. Then we can see the activity, just like we mentioned earlier, the units in curie or specific activity for radium-222 in picocurie per liter. Now, where can these radionuclides be found? For example, cesium can be found where there is a fallout. Cobalt-60 is utilized during cancer therapy, plutonium nuclear weapon, industrial radiography in industrial applications, probably to test the strength of materials and the durability of materials, if they can be used for their applications. We use iridium-192, which is a gamma emitter. So because of the gamma emission or the gamma radiation from iridium-192, it has very strong penetrating tendencies. So it can be used to test materials with appreciable thickness. So these are some of the applications. You can see technetium used in diagnostic imaging, americium for smoke detectors, and so on and so forth. So what are radiation hazards? Radiation hazards could be external or internal, and at the same time, they could be whole body or partial. So it depends on how an individual is exposed to radiation. The hazards could affect the whole body, and it could just affect some organs. And then contamination could occur through skin or through inhalation. If we have radioactive dust and it's inhaled, then we could have internal contamination. We could have contamination through ingestion, possibly of foods or food products, and through dermal openings, such as wounds on the skin. So what are the principles, radiation protection principles in health physics? There are 3 of them majorly: justification, optimization, and dose limit. Justification, optimization, and dose limit. What we mean by justification is that for any exposure to radiation, the most important thing is that you must have more benefits than detriments as a result of the exposure. And by optimization, we mean that, well, irrespective of the exposure, you must keep the dose as low as possible, even if you have some benefits. For example, in industrial radiography, but we try to keep the doses as low as possible. And then there is a particular dose that must not be surpassed, and that is the 3rd principle, which is the dose limit. So, but generally, radiation protection principle spans through time, distance, and shielding. By time, we mean that we should restrict exposure to radiation within a particular frame of time. And then by distance, what we are saying, if you look at the diagram there, the greater the distance from the source, the less the radiation received. And then by shielding, we are saying, well, if radiation is detrimental, then we can shield people away from the radiation sources. And that is very applicable in hospitals or in nuclear reactor facilities where we have shields to protect people and the environment. So in health physics, there are instruments that can be used to detect radiation. Some of them are handheld, and we refer to them as survey instruments, which most of the time are used for detecting contamination or exposure. For example, you have a health physicist coming from the hospital and from a treatment theater or something. So handheld instruments can be used just to do a quick survey to determine if the person has been contaminated and what the level of contamination is. We also have personal dosimeters that are used for individual monitoring. So as a patient or as a staff in the hospital, you can use these personal dosimeters to